Pro Electrician. Number 1. Chapter 1, Electrical Fundamentals Review. Technical terms of this chapter are alternating current AC, alternator, branched circuit, capacitance, conductors, current, direct current, electromagnetic induction, electromotive force or EMF, equivalent circuit, frequency, impedance, inductance, instantaneous voltage, insulator, nominal voltage, Ohm's law, parallel circuit, power, power factor, rated voltage, resistance, root mean square or RMS, voltage, series circuit, voltage, and work. The objectives for this chapter are to define the basic units for electrical voltage, current, resistance, energy, and power, calculate electrical power, discuss the characteristics of series, parallel, and complex circuits, calculate voltage, current, and resistance in series, parallel, and complex circuits, describe and compare alternating current and direct current, explain the functions of basic components of an alternator, explain the effects of inductance and capacitance in AC circuits, calculate power factor and impedance in AC circuits, describe the single-phase and three-phase electrical systems, recognize Y and delta configurations, and lastly to distinguish between nominal voltage and rated voltage. This chapter reviews the fundamental concepts of electricity. This review will help you master the material in this book. The material covered in this chapter is intended as a refresher for those already familiar with the basic concepts and fundamental electrical relationships. If you have no prior training or experience with electrical theory, this chapter will provide the basics and encourage you to pursue further study. Basic electrical circuit units. The flow of electricity in a circuit can be compared to the flow of water through pipes. There are several measurable quantities associated with water flow. There is the rate of flow, the force pushing the water through the pipe, and the opposition to the flow caused by friction with the pipe. An electrical circuit has similar characteristics. The rate of flow of electricity is called current. The force pushing the electricity is called voltage. And the opposition to the flow of the electricity is called resistance. These are the basic units of electricity. Current. All matter is made up of tiny particles called atoms. Each atom has a central nucleus around which electrons orbit in much the same way as planets orbit around the sun. Depending on the type of atom and its structure, some electrons are free to move to other nearby atoms. Under normal conditions, this occurs randomly without any specific direction or net gain or loss within the substance. If an electron force is applied to the substance, the electrons can be pushed in one direction. This directional movement is current. Thus, current is to electricity as flow is to water. Certain substances, particularly metals, are composed of atoms that have many easily moved electrons. These substances, such as silver, copper, and aluminum, are called conductors. Other substances, such as rubber, plastic, and wood, are composed of atoms with few easily moved electrons. These substances, which resist electron flow, are called insulators. They are enabled to carry a current. Current is measurable in quantity, or current is a measurable quantity. The number of electrons that flow through a conductor in a given amount of time is measured in units called amperes. 1 ampere is equivalent to 6.5 times 10 to the 18th electrons passing a given point in 1 second. Amperes are usually abbreviated as amps, or simply in capital A. The symbol used in formulas to represent current is the letter I. Voltage. For a current to flow in a conductor, a force must be applied at one end. This electron pushing force is called the Electro-Motive Force, or EMF. This force can be produced in various ways, chemically, mechanically, or by other forms of energy, such as sunlight. Specific examples are batteries, chemical, generators, mechanical, and photovoltaic cells, sunlight. Voltage is a measurement of the EMF produced by a source. The volt, symbolized with a capital V, is the basic unit. It is defined as the potential difference between 2 points in an electric circuit when the energy needed to move 1 ampere between the points is 1 joule. Notes: in formulas, voltage is represented by either capital E or capital V. The capital E will be used in this text. Resistance. The opposition to the flow of electrons through a circuit is called resistance and is measured in units called ohms. The symbol for ohms is the Greek letter omega. 1 ohm is defined as the electrical resistance that allows 1 ampere to flow when 1 volt is applied. For an electric circuit having a constant resistance, the current and voltage are directly related. That is, if the voltage is doubled, the current will double. If the voltage is increased 10 times, the current will increase 10 times. Thus, for any given circuit with a constant resistance, the ratio of voltage to current is constant. This relationship is called Ohm's law and can be expressed mathematically as shown on the screen, where R, or resistance, equals to E, or EMF, divided by I, or current. As we go on, we will see how Ohm's law is applicable to many types of problems involving electrical circuits. Power, energy, and work. The basic purpose of an electric circuit is to perform work. Work is the process by which energy is transformed from one type to another. For example, an electric motor performs work by changing electrical energy into mechanical energy. Any form of energy has the ability to do work. Both work and energy are practically identical and can be thought of interchangeably. Power is the rate at which energy is transformed. It is the rate of doing work. Electric power is measured in watts, symbolized by a capital W, and it is the product of voltage times current. Since a watt and a volt ampere are the same, power is often expressed in volt amperes, or VAs. Power is expressed mathematically as shown on the screen, where P, or power, equals to E, or EMF, times I, or current, or power equals to current squared times resistance. Basic circuits. Simple and complex circuits are composed of the same components. All circuits must have a source, a device, and a conductor. The source provides the electromotive force, the device resistance or elements. These terms are equivalent, uses the energy to perform some desired function. The conductor, most often a wire, carries the current from the source to the device back to the source. Other components found in a circuit are controllers, such as switches, and circuit protection, such as a fuse or circuit breaker. A very basic circuit is shown in figure 1-4, shown on the screen in the middle. There are several types of circuits. The various types are differentiated by the arrangement of the resistors and other elements. There are series circuits, parallel circuits, and complex circuits. Series circuits. A series circuit, figure 1-5, is a circuit in which the loads are connected in such a way that there is only one current path. As shown in the illustration, the currents must pass through the first resistor, then the second, and then the third before returning to the source. These are the characteristics of a series circuit, where the current or I is the same through every element and every resistor in the circuit, where I total equals, for example, I1 equals I2, I3, and so on. The voltage across each resistor is a product of the current times the individual resistance. Recall Ohm's law, where E equals to I times R. The voltage across each resistance can be different. However, the total voltage must be equal to the sum, or must be equal the sum of the individual voltages across the resistors. For example, E total equals to E1 plus E2 plus E3, and so on. The total resistance of the circuit is the sum of the individual resistances. For example, R total equals to R1 plus R2 plus R3, and so on. Finally, Ohm's law is applicable to any part of the circuit or to the circuit as a whole. This is the extremely important point to remember. It is the key to understanding and solving circuit problems, especially complex circuits. The following example illustrates the characteristics and relationships of a series circuit and how Ohm's law is used to solve circuit problems. Sample problem 1-1. Using the following figure, calculate the current flowing through the circuit and the voltage at each resistor. The formulas used are shown top of the screen, where IT equals to ET divided by RT. RT equals to R1 plus R2 plus R3. IT equals to I1 equals to I2 equals to I3. And finally, EN equals to IN times RN, which equals to IT times RN. The solution is that the current can be calculated using the formula IT equals to ET divided by RT. Again, T stands for total, and you already know the symbology for the other electrical values, such as I for current, E for EMF or voltage, and R for resistance. To find the total resistance, add the individual resistances together, as shown on the screen, which in this case equals 60 ohms. So the voltage is 120 volts, so that the current is equal to, using the formula, IT equals to 120 volts divided by 60 ohms, in this case is 2 amps. The voltage at each resistor can be calculated using the fact that current is constant throughout the circuit. For example, I1 equals to I2 equals to I3, etc. This is the current total, or IT. Therefore, E1 equals to I1 times R1, or in this case, I total equals to R1 times R1 equals to E1. In this case, 2 amps times 20 ohms equals 40, which in this case is 40 volts as the answer. E2, again, that's the voltage at resistor number 2. In this case equals to I2 times R2, which is interchangeable with IT times R2, which in this case is 2 amps times 10 ohms, or 20 volts. I3 equals to I3 times R3, or IT times R3, which in this case is 2 amps times 30 ohms, or 60 volts. The current flowing through the circuit is 2 amps, with resistor voltages of 40 volts E1, 20 volts at E2, and 60 volts at E3. Series circuits are rarely encountered in practical commercial, residential, or industrial wiring applications. These circuits have several inherent problems. First, any change of a resistance in the circuit affects the current throughout the circuit. Thus, in turn, changes the voltage across the other resistors in the circuit. Second, if any part of the path is broken or opened, the circuit is dead from that point on. If one element fails, the entire circuit is shut off, or at least part of it. Third, switches or other controlling devices cannot be used for individual loads within the circuit. If one load is turned off, all loads lose power. Again, or at least some loads may lose power. Fourth disadvantage is that voltage across any load depends on the overall circuit arrangement. It is almost impossible to design circuit devices that can operate at so many different voltages. Here's a look at characteristics of parallel circuits. The voltage across all branches of the circuit is the same as the total voltage at the source. For example, E total or EMF total equals to the power or the voltage at A, the voltage at B equals to the voltage at C, and so on. The total current is equal to the sum of the currents flowing through each of the branches. Thus, the current total is equal to the current at point A plus the current at point B plus the current at point C. So the current total is additive. The total resistance in a parallel circuit is the reciprocal of the sum of the reciprocals of the separate branch resistance. That is a mouthful, but to express this in a much cleaner or clearer manner, let us look at it mathematically, where 1 divided by the resistance total equals to 1 divided by the resistance number 1 plus 1 divided by the resistance number 2 plus divided 1 the resistance number 3, and so on. Ohm's law applies to the entire circuit and any of the branches. This is for parallel circuits. Any opening or break of a branch does not stop the current flow through the other branches in parallel circuits. For this reason, parallel circuits have a distinct advantage over the series circuits discussed earlier. Again, parallel circuits. A parallel circuit is one in which the elements are arranged in such manner that there are several paths for the current. As seen on the figure on the screen now, a parallel circuit. In electrical circuits, the term parallel does not necessarily mean physically or geometrically parallel, but merely signifies alternate routes or branches. That's very important. Parallel circuits are often called branched circuits. That's why when solving for parallel or complex circuits, you must imagine or think of the different branches or parallel branches in your head and rearrange them, no matter what shape they may be on. If they could be rearranged as parallel, you should go on and do that, even if it's on a sketch or even in your head. And you'll find out about this here shortly. Notice that the characteristics of a parallel circuit are in many ways opposite to those of a series circuit. The following example illustrates the relationships at work in a parallel circuit. In the problem shown on the screen, using the following figure, find the current through each resistor. find the total current of the circuit, and finally find the total circuit resistance. Formulas used are ET equals to E1 equals to E2 equals E3. Also, current at 1 equals to the EMF at 1 and over the resistance at 1, or divided by the resistance at 1. And finally, the resistance at 2 equals to the EMF at 2 divided by the resistance at 2. The solution for the first part of the problem, where EMF T, or total EMF, equals to E1 equals to E2 equals to E3, which in this case is 120 volts. For the currents at 1, we divide 120 volts by 10 ohms. In this case, we get 12 amps. The current at 2, we divide 120 volts divided by 30 ohms. In this case, 40 amps. Finally, at current number 3, is the same as 120 volts divided by 20 ohms, or 6 amps. Part B of the formula, current total equals to current at 1 plus current at 2 plus current at 3. The solution is the total current equals to 12 amps plus 4 amps plus 6 amps, in this case 22 amps. C, part C formula is 1 divided by the resistance total, which is equal to 1 divided by the resistance at 1 plus 1 divided by the resistance at 2 plus 1 divided by the resistance at 3. Solving for this formula is 1 divided by RT equals to, in this case, 1 divided by 10 ohms plus 1 divided by 30 ohms plus 1 divided by 20 ohms. And working out the formula, as you can see on the bottom of the screen shown now, we ultimately get 5.45 ohms. You can go through and see the steps, work out the formula yourself to your satisfaction. Arranging elements in a parallel circuit is far more practical than arranging them in a series circuit. Devices are subject to almost no adverse effects from other elements, as is the case with series circuits. Complex circuits. Most circuits are not simply series or parallel, but a complex arrangement consisting of series and parallel portions. A series combination circuit can be broken down into an equivalent circuit by applying the concepts mentioned previously. Shown on the screen is sample problem 1-3. Refer to the following complex circuit. The source voltage is 12 volts. What is A, total resistance, B, total current, and C, voltage across each resistor? For this problem, we use formulas 1 divided by the resistance at EQ, which equals to 1 divided by R3 plus 1 divided by R4. And the other formula we use is the resistance total equals to the resistance at 1 plus the resistance at 2 plus the resistance at EQ. The solution: think of the circuit as a series circuit where R1 is the first resistor, R2 is the second, and R3 and R4 combine to make the third resistor. You can see this in the middle of the screen, shaded by blue. The total resistance of the two parallel branches, R1 and R4, are equivalent resistant, or is the equivalent resistance. The equivalent voltage is the total voltage in the parallel branches, seen by the formula 1 divided by Req, which equals to 1/6, or 1 divided by 6 ohms, plus 1 divided by 12 ohms. Working through the formula, as you can see on the bottom of the screen, you get 12 ohms. working the problem using the formula current total equals 2 EMF total divided by resistance total. In this case, we get current total equals to 12 volts divided by 12 ohms, or 1 amp. Continuing on working the formula, we use the current at 1, which equals the current at 2, which equals the current at EQ, which equals the current total. And we also use formula E, or EMF at 1, equals to the current at 1 times the resistance at 1. We also use the formula, the EMF at 2 equals to the current at 2 times the resistance at 2. We also use the formula, the EMF at EQ equals to the resistance, the current at EQ times the resistance at EQ. Finally, we use the EMF at 3 equals the EMF at 4, which equals to the EMF EQ. The solution for these formulas are seen at the bottom of the screen, where the current at 1 equals to 1 amp, the EMF at 1 equals 1 volt, the EMF at 2 equals 7 volts, EMF at EQ equals 4 volts, EMF at 3 equals 4 volts, and EMF at 4 equals 4 volts. You can see the working out of the formula at the bottom of the screen to your satisfaction. Notice in sample problem 1-3 how the summation of the voltage across each of the resistors within the equivalent series circuit is equal to the source voltage. The power is also conserved, where power total equals to EMF total times current total. In this case, 12 volts times 1 amp, which equals 12 watts. Or the power at 1 equals, the power at 1 plus power at 2 plus power at EQ equals to EMF at 1 times current at 1 plus the EMF at 2 times current at 2 plus EQ, the EMF at EQ times the current at EQ. Plugging in the values, we ultimately get 12 watts. The two power values are equal to the various characteristics of electric circuits, and these are summarized in figure 1-7 shown on the screen now. I highly suggest that you commit these to memory and understand the relationships or characteristics of each type of circuit. For example, in series circuits, all of the resistances and the voltages are always additive, while the currents are always the same as the total. While in parallel circuits, both the resistances and the voltages are the currents and the current is additive, and the resistances are not additive, but they are their reciprocals are additive, and the voltages are equal to the voltage total. So if you notice, the current total and the voltage total swap in each of the circuit types, while the voltages do the same, they swap. So voltages are additive for series and they're equal for parallel. The currents are equal for series and are additive for parallel. That is just one way to memorize these and always remember, keep them in your short-term and long-term memory. These will become very useful throughout your electronics or electrical professional career. The all-important alternating current, or AC. Alternating currents has current constantly changing direction and voltage continuously, changing value and polarity. Therefore, just understanding voltage, current, and resistance is not enough, as it is with direct current. We must be familiar with how alternating current is generated and its inherent characteristics and relationships. Alternating current is produced by generators and then distributed by a vast transmission system to plants, commercial buildings, and homes, and more. Alternating currents is easier and less costly to generate than direct current, or DC, and is conveniently distributed. In addition, the voltage and current can be altered using transformers to suit specific requirements. Electromagnetic induction. When a conductor is moved across the magnetic field, as shown in figure 1-8, an electromagnetic force is produced in the conductor. If the conductor forms a closed loop or circuit, the EMF will cause a current to flow around this loop. This is referred to as electromagnetic induction. In a generator, conductors form loops or circuits that are moved through a magnetic field. This creates a source of EMF. See figure 1-9. Alternators. An AC generator or alternator consists of several parts. Figure 1-10. The following is a brief description of 4 basic parts. First, the coil or armature rotates. Its conducting wire cuts across a magnetic field. The electron flow begins in this part. Second, the stationary poles, sometimes called the stator, create a necessary magnetic field. In some generators, the poles are magnetized by a portion of the electrical current generated. Third, the metal slip rings are always in contact with one of the terminals of the coil or armature. They transfer the current to the brushes. Fourth, the brushes transfer current from slip rings to the external circuit. One brush is in contact with each slip ring. Alternator operation. As the armature is turned, it cuts through the magnetic field created by the field magnets. Electrons flow through the wires of the armature. The electrons move into one of the slip rings, then to one of the brushes, and finally into the external circuits as shown in figure 1-11. Every half turn, the electron flow reverses. Then the electrons flow out to the external circuit through the opposite slip ring and brush. This creates the reversal of electron flow that accounts for the alternating current. The speed at which the generator is turned determines the frequency of the current. One complete turn is called a cycle. Figure 1-12. Frequency is measured with units of hertz or Hz, which represent cycles per second. In the United States, the frequency of alternating current is 60 hertz. Instantaneous peak and effective voltage. Instantaneous voltage is the voltage at a particular instant. For example, looking again at our sine wave or sine curve, the maximum positive voltage occurs at 90 degrees and the maximum negative voltage occurs at 270 degrees. These instantaneous voltages or voltage values are particularly important since they also represent the peak positive and negative voltages. Another important instantaneous voltage occurs at 45 degrees and 135 degrees in the positive part of the cycle, and again at 225 and 315 degrees during the negative part. The voltage at these points is referred to as effective voltage or root mean square RMS voltage, and is equal to 70.7% of the peak voltage. Nominal voltage, such as 120 volts or 240 volts, refers to the effective voltage of a circuit. Voltmeters read the effective voltage of a circuit. Equipment is rated for the effective voltage. Calculations are specifications are made using the effective voltage values. Phase relationship. In AC circuits, the voltage and current vary continuously with time. This relationship is often called the phase relationship. If alternating current is run through a purely resistive circuit, both voltage and current, although changing, will vary together and are said to be in phase. Figure 1-13. However, most circuits contain components that cause the voltage and current to be out of phase with each other. Figure 1-14. For instance, where the current lags behind the voltage, that is, the current reaches its peak after the voltage has reached its peak. This is a lagging current. The other circuit conditions might cause the current to peak ahead of the voltage, as illustrated in figure 1-15. Inductance. Inductive devices are another component of AC circuits. These devices create electromagnetic fields that decrease the response speed of the circuit. The most basic and useful type of inductive device is a coil. A coil is a conductor formed into a series of loops that may have a solid movable core. Figure 1-16. Electricians working with lighting controls are familiar with the variable inductor, another name for a coil. As illustrated in figure 1-17, the lighting brightness is controlled by inserting or withdrawing the iron core. The coil has the least inductance when the core is withdrawn and the greatest inductance when the core is fully inserted. Current is greatest when inductance is the least. Inductance opposes any change in current flow. If the voltage across a coil increases, the current flow increases slowly due to the self-induced voltage, which opposes current change. Conversely, if the voltage across a coil decreases, the current value decreases gradually due to the self-induced voltage. The major difference between an AC circuit with resistance alone and one with induction is response speed. The current flow in a circuit having only resistance will change instantly if the voltage changes. Current flow in an inductive circuit will respond slowly if a voltage change occurs. This opposition to inductance is called inductive reactance. It is measured in ohms as it is resistance. The symbol for inductive reactance is XL, L for inductance, which is measured in units called henries, or capital H. An inductance of 1 henry is present if 1 volt is applied to an inductor and the current flow increases at a rate of 1 ampere per ohm per second. Again, an inductance of 1 henry is present if 1 volt is applied to an inductor and the current flow increases at a rate of 1 ampere per second. Ohm's law is applied to a circuit with pure inductance, which can be rewritten as follows, where current equals to EMF divided by 2 times pi times frequency times inductance, or EMF divided by inductive reactance. In other words, resistance is a purely inductive circuit. It is due to inductive reactance, and it is numerically equal to 2 times pi times frequency times inductance. One key idea is to remember about purely inductive circuits is that the current lags the voltage by 90 degrees. Again, inductive circuits have current lag voltage by 90 degrees. Also, since inductive reactance increases or decreases with the frequency of a circuit, it has the same effect as resistance and impedes the current flow. Capacitance, symbolized by capital C, is the conditions whereby a circuit stores electrical energy. This occurs whenever there are two conducting materials, such as metal plates separated by an insulating material, such as air or paper. A device specifically constructed in such manner is called a capacitor or a condenser. Figure 1-18 is a simple representation of a capacitor. If a source of direct current is connected to the two plates of a capacitor, the current will flow initially, but then gradually decreases to zero. The electrical energy will be stored in the capacitor. The capacitor is then charged. If the source is not disconnected and the two plates are connected by a wire or resistor, current will flow through that connection for a limited time. When the current reaches zero, the capacitor is discharged. However, a capacitor in a DC circuit cannot maintain a charged condition because the current flows in one direction only. In an AC circuit, the voltage is constantly changing direction. The current is initially in one direction, charging the capacitor, and then in the opposite direction, discharging the capacitor. Therefore, current continues to flow, alternating back and forth. The capacitor plates charging and discharging. The unit of measure of capacitance is the farad, represented by capital F. Capacitive reactance, represented by XC, is the opposition to the flow of current due to the capacitance of the circuit. It is measured in ohms, just as is inductance and reactance. Just as is inductance and resistance. In a purely capacitive AC circuit without any inductance or resistance, the current will lead the voltage by 90 degrees. Again, in a purely capacitive AC circuit without inductance or resistance, the current will lead the voltage by 90 degrees, or by a quarter of a cycle. Mathematically, the value of the capacitive reactance circuit is as shown on the screen, where capacitive reactance equals to 1 divided by 2 times pi times frequency times capacitance. Ohm's law is applicable to a purely capacitive circuit and is expressed as shown on the bottom of the screen, where current equals to EMF divided by capacitive reactance, which is equals to 2 times pi times frequency times capacitance times EMF. Impedance. In AC circuits, the total resistance is the result of a combination of opposing factors. Some circuits have inductance and resistance, some have resistance and capacitance, and others have all three factors. Impedance, represented by capital Z, is the total opposition to the flow of alternating current. Impedance in a circuit can be calculated using the following formulas. For a circuit having resistance, inductance, and capacitance, Z is equal to the square root of resistance squared times, resistance squared plus inductive capacitance minus inductive reactance minus capacitive reactance, all to the second power. For a circuit having resistance and capacitance, impedance equals to the square root of resistance squared plus capacitive reactance squared. For a circuit with resistance and inductance, impedance equals to the square root of resistance squared plus inductive capacitance squared. For a purely resistive circuit, the impedance equals to the resistance. For a purely capacitive circuit, the impedance equals to the capacitive reactance. And for a purely inductive circuit, impedance equals to the inductive capacitance. Finally, impedance represents the total resistance in a circuit. So Ohm's law for AC circuits becomes impedance equals to EMF divided by current. The power factor. As noted earlier, power in a DC circuit is the product of voltage and current. In most AC circuits, determining the power is a bit more involved, requiring that the power factor be considered. The power factor is the ratio of the true power to the apparent power. It is expressed as a decimal or as a percentage. The power factor may be anywhere from 0 to 1.0 or from 0 to 100%. Recall, as noted earlier, that power is calculated by multiplying the current and voltage. This still holds true for DC circuits as well as AC circuits in which the current and voltage are in phase and all energy from the current and voltage are in phase. This still holds true for DC circuits as well as AC circuits in which the current and voltage are in phase and all energy from the source is fed into the external circuits. However, when the current and voltage are out of phase, this is quite often the case, with practical AC circuits. Some energy is fed back from the source to the external circuit. In this case, simply multiplying voltage and current would not represent the actual power. In fact, such a value is called apparent power. The apparent power is determined by measuring the voltage with a voltmeter, the current with an ammeter, and then multiplying the actual readings. True power, on the other hand, is measured with a wattmeter. Then, to find the power factor, the following formula is applied, where the power factor equals to true power divided by apparent power. As an example, problem 1-4, in the circuit shown, true power, as indicated by the wattmeter, is 1900 watts. The ammeter reads 10 amps and the voltmeter reads 240 volts. What is the power factor? The formula used as the apparent power equals to voltage times current, and the other formula is power factor equals to true power divided by apparent power. The solution using the first formula, we have apparent power equals to 240 volts times 10 amps equals to 2400 VAs. Using the power factor formula, we have 1900 watts divided by 2400 VAs, which is our apparent power. That division gives us 0.79, as seen on the bottom of the screen. A low power factor, as in our example, can be improved by certain corrective measures, such as changing various system components and installing capacitors. Utilization voltages. There are 5 basic voltages delivered from utility supplied distribution. The commercial building application depends on load requirements and economic considerations. First, the single-phase 3-wire system. Although the most commonly used in residences, it is often applicable to small commercial buildings and apartment complexes. See Figure 1-19. The 240 volt portion can be used for the larger power loads, while the 120 volt portion serves the lighting and receptacles. Second, the 3-phase 3-wire system is a common secondary system used in commercial buildings. This is a delta connected secondary with voltages of 240 volts, 480 volts, or 600 volts between phase conductors. The system is used when motor loads make up the majority of the overall load. Step-down transformers can be used to provide 120 volt service for lighting and receptacles. See Figure 1-20. The 3-phase 4-wire Y is the most common 3-phase system, particularly the type providing 120 208 volt service. This system can serve a variety of power and lighting load conditions. 4-wire 120 208 volt loads, 3-wire 120 208 volt loads, 3-wire 208 volt loads, 2-wire 208 volt loads, and 2-wire 120 volt loads. Figure 1-21 illustrates this highly adaptable and flexible system. Fourth, the 3-phase 480/277 volt 4-wire system is another extremely flexible variation of the 4-wire Y. It is a very economic commercial system and has advantages over the 120 208 volt system. This system provides for 3 types of loads: 277 volt single phase, 480 volt 3-phase, and the 120/208 volts or 120/240 volt loads, with the addition of a step-down transformer. Figure 1-22 shows the 480 277 volt 4-wire Y configuration. Fifth, the 3-phase 4-wire delta system is basically a modification of the 3-phase 3-wire delta. In this arrangement, the grounded neutral is added as a center tap to one of the secondary transformer windings, as shown in Figure 1-23. Caution: in a 4-wire delta system, the phase that is not connected to the tapped winding is called the high leg. The voltage difference between the high leg and the neutral is greater than the difference between the other phases and the neutral. The high leg conductor must be identified with orange marking to prevent an electrician from mistaking it for one of the other phase conductors. Very important to remember. There are other system configurations used for both commercial and industrial applications. However, they are essentially derived from these 5 basic types just discussed. Phase is represented by the Greek letter that looks like a slashed zero. The wire is abbreviated with a W, and a Y system is designated with the letter Y. For example, a three-phase, four-wire, 120, 208-volt Y system is abbreviated as 3, the symbol for the phase, which is a slashed 0, comma, 208 Y, 120 V for volts, comma, 4 W for 4 wires. Voltage standards. Nominal voltage indicates a desired level of the supply voltage for the electrical system. Rated voltage is the preferred voltage for the equipment, particularly motors. Commercial electrical systems are within the category of low and medium voltage. High voltage is reserved for power company distribution systems. The table in figure 1-24 lists the nominal and rated voltages for low and medium voltage categories as issued by the American National Standards Institute, ANSI. Here again is that a very important notification about the high leg on a 4-wire delta system that is not connected to the tapped winding. The wire that is not connected to the tapped winding is the high leg. Going through the review questions in this presentation and the following presentations. I will not be discussing these. I will show them on the screen as I have worked them out independently. So I will leave it up to you to review these on your own, pause the video as necessary, and do work the math several times if needed to become familiar with some of the calculations presented here. Congratulations, you have finished this lesson. Please do review and complete all questions as needed and perform problems as needed, and do move on to the next lesson. Thank you very much.